Today I'm going to discuss the principles and theory on the free moment equation as well as the derivation of the equation. The general free moment equation is given by, let's consider continuous beam shown below. So let's consider the portions A, B, and C. Let's draw the elastic curve and the moment diagram due to the internal moments of A, B, and C, as well as the moment diagram due to the loading. And for span AB, we will call the span as L1. For span BC, let's call it L2. And moment of inertia on span AB is E sub 1 and on span BC as E sub 2. So this is the elastic curve. Then from point B, we draw two lines. One is the tangent line and the other one is a horizontal line which serves as the reference for computing the displacements at A and C. So this is the horizontal line through B and another line at B on the elastic curve, the tangent line. So that we have two similar triangles, this triangle here, right triangle, and another right triangle here. We learned that from area movement theorems, the vertical deviation or distance of a point on the elastic curve from a reference tangent line, which in this case B, is denoted by deviation of A relative to B. We will call this distance of point A on the elastic curve from the reference horizontal line through the middle point B as HA, and the vertical distance of point C on the elastic curve from the horizontal line as H sub C. While the vertical distance of point A on the elastic curve from the reference tangent is deviation of A relative to B, and this angle is theta B, which is also equal to this angle here, theta B. So let's call this H sub C from the horizontal line, and the distance of point C from the reference tangent at B is the deviation of C relative to B. Let's draw the internal moment diagrams at due to the moments at A, B, and C over EI. So this is moment at A divided by E1 I1, moment at B divided by E1 I1. Assuming that the moment of inertia and I of span BC is greater, so that it will fall a little MB over E2 I2, and this is MC over E2 I2. Let's divide this diagram into two triangles. These are trapezoids. We divided into two triangles so that we can compute the area conveniently as well as the location of the centroid. This is the load moment diagrams over AI. So in general, let's just consider the figure shown. Then, of course, the centroid of the area in the left on span AB from A is the distance is denoted by small letter A. So we call this area 1 over E1 I1. That's the centroid of the area, and the distance of that centroid from point A is small letter A. Likewise, this is area 2 due to the loading diagram, and divided by E2 I2, and the distance of its centroid from the right point C is small letter B. So by similar triangles, This is HA minus division of A relative to B as to L1 is similar to this triangle here. Division of C relative to the tangent at B. So this triangle is similar to this triangle. So this leg of the right triangle is division of C relative to B minus H sub C. So HA minus division of A relative to B as to L1 equals division of C relative to B minus H sub C as to L2. Then rearranging HA over L1 minus division of A relative to B over L1 equals division of C relative to B over L2 minus H sub C over L2. The meaning of division of A relative to B is from area moment theorems. The moment of area on portion AB with respect to A. So the area of this trapezoid here, let's decompose it into two triangles and the area due to the loading. Then HA over L1 plus H sub C over L2 equals division of C of A relative to B over L1 plus division of C relative to B over L2. So substitute the value of division of A over L1 as equal to 1/2 of L1 times MA over E1 I1 times L1 over 3 plus this area here 1/2 L1 MB over E1 I1 times moment arm 2/3 of L1 plus area 1 over E1 I1 times A plus divided by L1 plus division of C relative to B over L2. This division of C relative to B is simply the moment of the moment diagram by parts of the portion from B to C with respect to C. So considering first this area, which is 1/2 of L2 times MB over E2 I2, then the moment arm is 2/3 of L2 plus 1/2 of L2 times MC over E2 I2 times L2 over 3, then plus this area 2 over E2 I2, moment arm is B divided by L2. Then combining like terms, especially for MB here, and simplify it, cancel out L1. So HA over L1 plus H sub C over L2 equals MA L1 over 6 E1 I1 plus 2MB, factor out, then we have L1 over 6 E1 I1 plus L2 over 6 E2 I2 from here plus MC over L2 over 6 E2 I2 plus area 1A over E1 I1 plus area 2B over E2 I2 L2. So multiply everything by 6 and let's transfer the right side. Let's make the right side terms in the left side terms and the left side terms to the right side terms. Multiply everything by 6. So MAL1 over E1 I1 plus MB times L1 over E1 I1 plus L2 over E2 I2 plus MCL2 over E2 I2 plus 6A1A over E1 I1 L1 plus 6 area 2B over E2 I2 L2 equals 6 times quantity HA over L1 plus H sub C over L2. So this is the general three moment equation when spans AB and BC have different material characteristics. So this is the general three moment equation. So remember that area 1 is the moment The area of the moment diagram due to the loading. MA, MB, MC are internal moments. HA is the distance of point A on the elastic curve from the reference tangent, which is the middle point of span ABC. Remember that? It is positive if A is above the reference horizontal tangent. H sub C is the vertical distance of point C on the elastic curve from the reference horizontal line. So normally, E1 and E sub 2 are equal or common. So if we multiply everything by E1, which is equal to E2, which we call in general E, the three-moment equation reduces to. So for the case E1 equals E2 equals I2, so we have MA L1 over I1 plus 2MB quantity L1 over I1 plus L2 over I2 plus MC times L2 over I2 plus 6A1A over I1L1 plus 6 area 2B over I2L2 equals 6E quantity HA over L1 plus H sub C over L2. So this is the three-moment equation when E1 equals E2 equals constant. But you only familiar one, the first formula should be remembered. The second case follows from the above, and the special case when both E1 and I1 is constant. So this time when I1 equals I2 equals I equals constant, then multiplying everything by I, and take note that I1 equals I2, the equation reduces to MAL1 plus 2MB quantity L1 plus L2 plus MC times L2 plus 6A1A over L1 plus 6A2B over L2 equals 6EI quantity HA over L1 plus H sub C over L2. So that's it. This is the case when I1 equals I2 equals constant for that case. But as I said, you should familiar the general case, which is the first formula, because all the other two cases are from this general three-moment equation. Now, how to compute 6A1A over L1 and 6A2B over L2? So all you have to do is treat the span as simply supported, then evaluate 6 over L or 6 over L1, then the area of the moment diagram. If it is positive, positive, then distance of that moment diagram from the left. Then A is distance of the centroid of that area 1 from the left. Then area 2 is moment of area due to the loading, and you should take moment about the right side. B is the moment arm or the distance of the centroid of the right span with respect to the right point or right end C. So you have to, these are the steps, construct the moment diagram by parts as shown. So for instance, we have this simply supported beam, because even if it is not simply supported beam, you have to treat that as simply supported beam. Then the reaction at A is, or the moment of the load P about B is PB. So the moment of the reaction at A about B is also PB. So if you take moment about A, then the intensity of this moment is PA, which is negative. So therefore, the moment of the reaction at B must also be PA, because the moment at A is 0, because it is simply supported. Even if you compute for the reaction at B, the reaction at B is equal to PA over L. So PA over L times L is PA. So the technique is you don't need to compute for the reactions. Whatever is the moment due to the load at one wall, if If it is negative, then the moment due to the reaction must also be the same, and it is positive, as shown in the figure. Then take note that area 1 and area 2 are moment areas on a span, and these moment areas may be positive or negative. In this case, we have a positive area due to the reaction, and we have a negative area due to the moment of the loading. And A is the distance of the centroid of area from the left point, and B is the distance of centroid from the right point B. And after that, you just evaluate 6 over L, then area 1A, or 6 over L, area 2B. Then treat all spans as simply supported. So in this case, 6A1A over L1 is 6 over L because the span is L. The positive area is 1/2 of L times PA, or 1/2 L times PA. And the distance of the centroid of that triangle from the left, which is A, is L over 3. Then you subtract the area here, which is 1/2 A times PA, and the moment arm is 1/3 of A, so A over 3. So take note that the other area is negative. Factor out the common terms here, or common factors, which are PA over 6. So 6A1A over L equals 6 over L times PA L squared over 6 minus PA cube over 6. So the common is PA over 6. If we factor that out, then we have L squared minus A squared. We can cancel 6. So the formula for 6A1A over L1 due to the concentrated load is equal to, with respect to the left, is PA over L quantity L squared minus A squared. Similarly, if we compute the value of 6A2B over L2, assuming EI is constant by the way for this case, then it is equal to PB over L quantity L squared minus B squared. So just consider the pattern of the formulas. Then due to uniformly distributed load, of course, the moment of the loading is W times L over 2, which is negative, and the degree of the curve is second degree. So therefore, the moment of the reaction is also WL squared over 2. So to make the moment at A0, because that's simply supported. Even if it is not simply supported, you always treat the span as simply supported. So therefore, the value of 6A1A over L1 is 6 over L. Then area of the triangle is 1/2 of L times WL squared over 2. Moment arm is L over 3. Minus 1/3 of L times WL squared over 2. The distance of the centroid of the spandrel from the left, which is point A, is L over 4. Simplifying, that would give us a value of WL cube over 4. You simplify this, it will give you WL cube over 4. Then, another way of deriving these formulas is by considering the result of the simple case, which is due to this concentrated load. So we have to cut a strip so that we can have a differential concentrated load, dP, and it is equal to the area of the strip, which is W times dx. The distance of the center of the strip from the left, we will call that in general as x. So x is imagined as A, then B is L minus x. So by integration, instead of this diagram, we have 6A1A over L1 equals differential P, which is W dx. A is x, L is L, then quantity L squared minus A squared, which is x squared, but in integral form. So 6A1A over L1 equals integral of dP, differential P, A over L, quantity L squared minus A squared from the formula here. We replace dP by W dx, A by x, and evaluate the expression. So the integral of the first term, which is L squared x, is L squared x squared over 2. The integral of the second term is x times x squared, so negative x to the fourth over 4 from 0 to L. So L squared x squared over 2 minus x to the fourth over 4 from 0 to L. If you simplify this, it will give you the same result, that 6A1A equals over L1 equals 6a2b over L2 equals WL cube over 4. Or in general, 6a1a over e1 i1 L1 equals 6a2b over e2 i2 L2 equals WL cube over 4. Next, for triangular loading, the result, I will just directly put it into formula. You have to verify this by either drawing this diagram or by considering a strip and by integrating. So the value of 6a1a over e1 i1 L1 is in general 7WL cube over 80, and the value of 6a2b. So with respect to the nearer support of the loading, it's 7WL cube over 60. With respect to the farther support, with respect to B or with respect to C, it is 6a2b over e2i2l2 equals 8WL cube over 60. Now, do not simplify 8 over 60 to 2 over 15, although the result will be 2 over 15. The purpose of that so that you can easily familiar with the formula for triangular loading. Take note that this triangle is across the entire span of the beam. If the loading will not reach the end of the span, then you have to either draw the moment diagram by parts or integrate it. For moment, then the result would be 6a1a over L1. This moment here is clockwise is equal to 6a1a over e1i1 in general is m over L quantity L squared minus 3a squared sa left side. And if the moment is clockwise, like in the figure, if the moment is counterclockwise, you just replace m here by negative m and the formula remains the same. While the value of 6a2b over e2i2l2 at the right side is equal to m over L quantity 3b square minus L square. So that's it. For the rest of other loading conditions, you may practice or solve. So 6a1a over L1 is in general integral of the area of the strip, which is differential P. Then moment arm is A. It may be X or it may be L minus X divided by L. This is our guide. Times quantity L squared minus A squared. Likewise, the general formula. Likewise, for 6a2b over e2i2l2, you just replace A here by B, then also in this term by B. Let us derive the let us derive the equation for 6a1a over L1 and 6a2b over L2, assuming EI is constant, for a situation where we have a couple load. So this is the situation. So let's make B as the wall. So the moment diagram should appear to be rectangular or uniform moment M here. And of course, below would be R over L for M also. The moment due to the reaction at A should also be M. So that's M over EI, and this is also M over EI. So that 6a1a over L1 equals 6 over L times M times B, because the moment arm is from the left, so that distance is quantity L minus B over 2. Then moment of this load, which is below, minus 1/2 Lm times moment arm is 2/3 of M. So simplifying, we distribute MB, so we have 6 over L quantity MBL minus MB squared over 2 minus ML squared over 3. We factor out M over 6, so 61A over L1 is 6 over L M over 6 times quantity 6BL minus 3B squared minus 2L squared. Replacing B by its equivalent, which is L minus A. So we have m over L, quantity is 6 times B, this is L minus A, then minus 3 times B squared, or L minus A quantity squared, minus 2L squared. So simplifying factor, we have m over L times 6L squared minus 6AL minus, the first term is L squared, so minus 3L squared. The second term is negative 2EL, so times negative 3, so positive 6AL. The last term here is A squared, so times negative 3, so negative 3A squared, then minus 2L squared. Combining like terms, 6L squared minus 3L squared minus 2L squared is equal to L squared. Then we can cancel out negative 6AL and L squared. Then we have minus 3A squared. So that's the formula. M over L times quantity L squared minus 3A squared. So for 6A2B over L2, then it should be M over L quantity 3B squared minus L squared. This is here. Then let's consider the situation, which is the only unique way in computing deflection at a point where a couple is acting for three-moment equations. How do we compute the deflection at the point where the couple is acting? So the only unique way is, because supposedly we're going to consider the span as simply supported, A and B as simply supported, then it's confusing because we have different moment just to the left and just to the right of B. So instead, we draw the moment diagram by parts at B, and we call that delta B. The reaction here is reaction times 10 equals 120, so the reaction at A should be upward equal to 12 kilonewtons. So by the way, we draw horizontal line through B as our reference. So HA, which is delta B, equals H sub C, which is also delta B. And the reaction, as I said, is 12 kilonewtons upward at A, then downward at C, which is also 12 kilonewtons. And the moment diagram by parts will be 12 times 4 is 48, that's positive. And we have a counterclockwise moment here, so minus 120, but that becomes negative 48 minus 120 equals negative 72. Then it goes back to 0 there. So this is negative 72. That's the moment diagram by parts. So let's solve for 6A1A over L1 and 6A2B over L2. But before that, let's set up the three-moment equation, which is MA0 plus 2MB quantity L1 plus L2 plus MC, which is 0 times quantity L2 plus 6A1A over L1 plus 6A2B over L2 equals 6EI quantity HA over L1, which is 4, L1 is 4, and HA is delta B, plus HC, which is delta B also, divided by L2, which is 6. Now, in the three-moment equation, the moment at B is treated 0 because it crosses 0 moment, and secondly, we consider A, B, and BC as simply supported walls, and there should be no moment at the simple support B. So we still write this equation here, and we simply ignore NB to be 0. What we are going to compute will be 6E1A over L1 and 6E2B over L2. So 0 plus 2 times 0, as I said, then everything here is 0, MC is also 0, equals 6 for span AB, 6 over 4, then the area, moment of area with respect to the left is 1/2 of 4 times 48, then 2/3 of 4 is 8/3. Then for the second part, then we have 1/2, 6 over 6, 6 over L, then quantity 1/2 of 6 times negative 72. The moment arm is 2/3 of 6 with respect to C, or with respect to the right, so times 4. So simplifying these values, we will get delta B, which is equal to negative 100 192 over EI. What's the meaning of this? So this means that both A and C are below the middle point B, because the result is negative, so that means both A and C are below B, not above B. So that means that the deflection at B is positive. So delta B is 192 over AI positive, because in the explanation, we first imagine that HA and H sub C or delta B would be above the horizontal line through B. So imagine that B is here due to the loading. So automatic, we draw horizontal line through B, and delta A is treated positive here. Delta A is equal to delta B, by the way, treated positive. Imagine B is here, then delta H sub C is also delta B, which is above B, supposedly in the assumption. And because the result is negative, it means that both A and C are below. So this should be the position of B, so that both A and C are below the horizontal line through B. So that's why delta B is above B, or B is above A and C. So that's why delta B is positive 192 over A. So this is the explanation. MB is treated zero in the application of the three-moment equation because spans AB and BC are treated simple spans without a load in between their ends. So when there are no loads in between the ends of a simple span, it means that the moment at either support should be zero. So there will be no MB. So how do we, another explanation, the calculations of the value 6A1A over L1 and 6A2B over L2 must be based on the moment diagram when there is a couple as a load only. When there are any other loadings, then you should compute a separate value for 6A1A over L1 and 6A2B over L2. So for the slopes at A, B, and C, apply the double integration method, because the three-moment equation has no slope in the formula. So we should apply the double integration method. Anyway, we have already calculated the reaction at A, which is upon 12. Imagine a section here so that our moment equation is applicable for the entire span. So that our moment equation would be EI y double prime is equal to 12 times x, then minus 120, because it is located not at the origin but at the distance 4 meters to the right of point A, then it should multiply 120 by quantity x minus 4, then raised to 0, which is anyway equal to 1. But the purpose of that is, then depending on the value of x, if the value inside the parentheses is positive, then it is included, but if it is negative then or 0, then we simply ignore that term. Then integrating once, we have 6x squared minus 120 times x minus 4 raised to 1, then plus c sub 1. Integrating again, take note that A is a support, therefore there's no deflection when x is 0, so there will be no c sub 2. So EIY is equal to 2x cubed minus 60 quantity x minus 4 squared plus c sub 1x only. There's no c sub 2, as I said. Then when x is 10 at c, then y is 0, so we can solve c sub 1. And take note that c sub 1 is interpreted as the slope at A, because when x is 0, when we substitute it here, EI theta A equals, this is 0, this is ignored, then C sub 1. That's why theta A is C sub 1 over EI. So solving for this C sub 1 here, we get C sub 1 equals 16. So therefore, theta A is equal to 16 over EI. And that is positive, so therefore it is counterclockwise. Correct. Likewise, when x is 4, then we can compute theta B, substitute into EIY prime. So EI theta B equals 6 times 4 square. The second term is 0, then plus C sub 1 is 16. So solving for theta B is equal to 112 over EI. Then for x is 10, we can solve theta C. So when x is 10, y prime is theta C. Substitute into the formula for EI y prime. EI theta C equals 6 10 squared minus 120 times 6 plus C sub 1 is 16. So theta C is equal to negative 104 over EI. And that's it. Negative means the rotation of the tangent is clockwise, then positive means counterclockwise. These are the correct signs and correct values of the slopes at A, B, and C.